Francesca Lavazza, presidente del Castello di Rivoli.
Stai qui con me, stay with me, thanks. Buongiorno, benvenuti a tutti quanti. Welcome everyone. Sorry, I switch in English because I know there is a streaming, so everyone could follow us. And today is a very interesting day for the Castello di Rivoli, and especially because today will be discuss all forms of artistic energies. And the energy has always been generated by contact and interaction. And the conference aims today is to create new form of contacts, also bringing together artists, philosophers, scientists. And once again, the Castello di Rivoli Museo di Arte Contemporanea is an ideal place to inspire the new avant-garde of thought. So I would like to thank you, Caroline, to lead the discussion, and good work to everyone. Thanks.
Okay. So, welcome to Castello di Rivoli Museo d'Arte Contemporanea for energy cultures. Energies, imaginaries, currencies, and nuclear horizons of the planet. Prima di iniziare ci sono alcuni ringraziamenti istituzionali che sono assolutamente necessari e anche dovuti. Prima di tutto il Castello di Rivoli Museo d'Arte Contemporanea realizza le sue attività primariamente grazie ai contributi della Regione Piemonte. Oltre alla Regione Piemonte ci sostiene anche la Fondazione Cereti, la Fondazione Cereti per l'Arte, la Compagnia di San Paolo, la città di Torino che porta i suoi saluti con l'assessore Foglietta oggi e 1000 altre realtà. Vediamo cosa ho dimenticato, perché dimentico sempre. Certo. Allora, questo particolare evento è realizzato grazie alla, stavo per dire coevoluzione con, insomma, alla collaborazione di Nucleo e in particolare Stefano Buono, che ringrazio. So I'm switching back to English, and it all started, well, to be honest, it all started a long, long, long time ago, billions of years ago. But to be a little less honest, on a personal level, it all starts as a young woman 30 years ago, speaking with the Arte Povera artists. The Arte Povera artists are mainly from Torino, some from Genova, Firenze, Bologna, Rome, you know, the adopted city of the Greek artist Yannis Kounelis.
I leave your stage.
Oh, okay. Okay, thank you, Chairman. And I learned so much more from them than really at university or anything else. And talking with Giovanni Anselmo or Gilberto Zorio or Mario Merz, Marisa Merz, but all of them, also Fabio Paolini and Calzolari and the others, not with Pascali because he had died in spring '68, but talking with them, the main lesson from them was the artwork does not exist in any physical form, but it's not about dematerialization. Artworks are just a bunch of inert matter, or they're alive, and to be an artwork they have to be alive. And what does alive mean? It means that there is energy. So la parola energia, energy, was used by them to talk about their works, especially in a Heraclitean way of thinking, although Heraclitus didn't use the word energia, but he spoke of fire as the primordial source of everything that exists in the universe, as being something that is constantly transforming and changing and never inert. And it's interesting that that's not so far from Einstein fundamentally, I mean, in a way. But I hope that the physicists will correct that. and put everything else in the middle. Today, so years and years later, after that generation of people who were thinking about energy, and energy for the Arte Povera artist was not just, you know, electricity running through a neon tube for Mario Berz. It was also the vital energy, the movement that happens when you fall in love or you desire something. So on a very micro physical level of a body, of a vitality, to the energy that happens when your synapses fire and ideas are born, or when there's electricity as well, or there's fire like Cunelli's. It's all that makes up an artwork according to them. And at that time, this way of thinking was somehow not against, because they were not controversial, adversarial artists, but it was certainly not the same way of thinking of the minimalists or the pop artists of the time. But today, I would also like to thank the most important person for me in this conference, which is the artist Agnieszka Kurant. Because it all started in a conversation in a car when we were driving to visit the Trino Vercellese dismantled nuclear power plant, which closed down after the referendum in Italy banned nuclear energy production. And we were going to visit this place for our innate interest in everything that we don't know. And we were in the car with Stefano, and we said, well, the question of energy is among the most vital for the future of human and more than human life on the planet and the flourishing of life on the earth. So thinking about energies today, imaginaries, and also currencies, which is something that Agnieszka also always goes back to, and nuclear horizons means addressing the contradictions and unleashing the disruptive and transformative properties of energy that runs seamlessly through the works of art and scientific innovations. In an attempt to explore the potential scenarios of energy coevolution, it's necessary to investigate living matter at the scale of its atoms, or much, much smaller, their entanglement, communication, and interaction, attempting to challenge the static and conventional postulates about energy. So to bring artists and writers, scientists and philosophers, enthusiasts and skeptics together, architects, to think together for one day is kind of like an experiment. And we will know only later. Someone was asking me, but what is the result of this? Earlier this morning, I don't know what the result of it is. Usually the results are seen 20 years later, 10 years later. Sometimes the results are babies, you know, from an artistic event. People marry, sometimes divorces, and all sorts of things are the results of these kinds of meetings. But generally, culture and civilizations do change according to what also museums decide to engage with and decide to bring to the fore as discussions. So the responsibility in programming events or exhibitions is a huge one, because it has to do with the past in the future. So the heritage in the past, what we will be discussing 50 years from now, or in 1550, had to do with what the Medici were doing in 1480. So it is an important thing. So energy has shaped life on Earth. I'm taking a little time with this introduction because I see people wandering in. It was raining downtown, so I don't want them to miss the talks that will come. Civilizations and societies throughout history have been shaped through energy and how we use energy, but also pre-human civilizations. I mean, photosynthetic conversion of solar energy into biomass shaped what we call nature. And then humans have been shaped through fossil fuel combustion and later hydroelectric power plants, and the use of atomic energy since the mid-20th century has been able to produce heat that boils water, that makes the turbine work, that makes the electricity, has also been part of this scenario. And the energy field has also been a field of controversy also between different parts of the world and different peoples of the world, what we call today global north and global south, the responsibility for all the trash and for ruining parts of the world, peoples themselves through what we do and what other people do. So it's a big swirling of animal, vegetal, and physical forces, to go back to the arte povera way of thinking. And the current wish to abandon fossil fuel energies to contain the CO2 and their gradual replacement by renewable energies seems to coincide, interestingly also, with the dematerialization of money and its partial substitution with digital currencies, that something that Agnieszka also observes quite a lot, and the production of that money is also dependent highly on energy. And the word in cryptocurrency mining is gas, forms of gas. So all of these issues are important alongside the issues of climate change and climate crisis. But how we're going to do this or not do this is crucial. How we're going to move forward in the next 50 years is crucial. Our decisions, our plans, our projects, our lives, how we run them in terms of our relation to energy, its production and consumption, will shape maybe hundreds of years of this world. So it's a big responsibility, and I think that this responsibility should not be only the responsibility of politicians, who usually have short-term plans, electoral short-term plans, and should not be the responsibility only of scientists at all, because scientists sometimes play with God a little bit. And, we could have rabbit humans now easily if certain ethical issues had not been discussed and worked through, which then turned into legislation in terms of what in genetics we were allowed to do or not allowed to do. So it should be the responsibility, a co-shared responsibility of all of us, everyone who thinks, and a little bit less maybe of AI, because AI would probably wipe us off the planet in order to make a better balance between so-called nature and culture, given the population is a lot higher than it was when agriculture started on the planet. And that also was a moment of a big energy shift, because suddenly you had a lot of cultivated food. So another person I was speaking to last night mentioned the ambivalence of this whole question. And I said, yes, of course, it's ambivalent. I mean, we have to stay in the space of ambivalence right now, because, of course, fire warmed people and fire burned people. So the question is not, is fire good or bad, but how we use it. It's like psychoanalysis. The question is how we use it. Do we use it to manipulate people because we have more ability to read their body movements, or do we use it to better our own life and the life of others? So the last thing I would like to say, because I see that people have trickled in, the last thing I'd like to say is that Dante had it all down. Now, not to be a nationalist here, but Mr. Dante, he wrote the most fantastic poem called the Divine Comedy. And after 3 canti, at the end, you know, the last sentence of the last 33rd canto of the Paradise, he says, El sol, no, amor, that's it, that's what I was going to say. Amor che muove il sol e le altre stelle. Love that moves the sun and the other stars. And actually, that is not wrong from a physical and physics and scientific perspective. All of the emotional aspects, if you look at it on a subatomic level of entanglement, and then if you look at it on a biological level, it is transference of energy. So there we go to why I wanted to show the video that you just saw. The video you just saw, which I hope we will see again more at length now, is by Ash Thorpe, who is a digital artist living in California. And he is not with us here today because he doesn't move on Saturdays. He has a very particular way of organizing his life. So if it had been on Tuesday, he would have been here. But Saturdays is he, as a Stoic, he reads a lot of the Stoics. Saturday is not the day that he does talks. So he made a video for us, which is this, and it's called Diamond Eye. And it is trying to reproduce, according to his vision, the effects of psilocybin. So we don't have to take mushrooms, just watch it. And I would like it louder this time, and 5 minutes. Okay? Up there in the regia. Grazie. And then we talk. Thank you. Desidero, I would like to invite Stefano Buono, who is the tallest man I know, to say a few words from his perspective on this mad endeavor, which is not exactly the same as his daily life, I think. Or am I wrong?
Thank you, Caroline, sorry. Yes, I don't know if I'm going to do babies during this conference, but certainly I will not divorce, because my wife, she's a nuclear medicine physician, nuclear. And so I discovered with her how nuclear can be a good energy for the health of people. We developed drugs that are really impacting the life of the people. So you see, I liked your discussion about the fire. The fire can burn, but the fire can do a lot of things that are very good. So the key is finding, with nuclear, what is good for us and what is not. Certainly the bombs are not good at all. And I think that the argument of a nuclear bomb has influenced our understanding of nuclear. Because think about the fact that people who had a bomb, a country had a bomb, had to scare the other countries. So I think the narrative on this has been exaggerated in the past, on the consequence of radiation. It's been exaggerated in the past, created a gap, a cultural gap between the science and the people. And I welcome very much this meeting because, you know, it's part of what's happening today to fill again this cultural gap. People want to know more about this energy. Everyone, including the artists and philosophers and writers that are here today with us. So thank you, Karen, for organizing this meeting, and thank you to the Castello di Rivoli of doing that. But the nuclear narrative of the past that has been also exaggerated by the enemies of the nuclear, the lobbies of oil companies and so on, has maybe created something very positive. Nuclear has become the industry that is the safer in the world among the energy producing industries. It's a surprise for some of you to know, but it's the reality of the thing. And has pushed us to create even a safer way of using nuclear energies. So even not considering the past, if you look at the future, there are opportunities to use this energy that is not only good for the health of people when we treat people with nuclear energy, but is also a potential of really having a sustainable form of energy for the future. Today we might build reactors that can turn off by itself. They don't need a human intervention. They can shut down without any intervention, even with errors. That's and today we can use the nuclear waste as a resource, so we can.
That's what I was interested in.
Yes, and
Explain. That's what I was most interested in, because if we were just making the same old nuclear reactors as before, I myself would be very skeptical, because we would be mining more uranium and we would be enriching more uranium. So could you explain this concept which drew me to learn about what you do?
yes, I think Luciano will get a little bit into the details. We have today the possibility to listen to many people, and I don't want to take the floor on that. Just introducing a little bit the arguments. So a nuclear that is much safer, wow, that is cheaper, because it's also the economy plays a role, and what is really more important is that it cleans up what has been done in the past 70 years, probably pushed by the misuse of the nuclear part of the nuclear waste, the plutonium, to make the bombs. They're creating a lot of, and today for thousands of years we can just live with the waste that we have, with the uranium that has been extracted from the earth. So it's a huge opportunity to make a more sustainable approach to the production of energy. So this is just an introduction of a long discussion that we'll be having over the day. So thank you everyone for coming, and I give the microphone back.
Okay, thank you, Stefano. So we'll learn about how to use, I mean, I say this in full disclosure, obviously. That's why we've invited Stefano to speak, as well as having supported this event. What I was very interested in is the concept of using spent fuel, nuclear waste, as the fuel in these new reactors, and therefore what would be the waste of the waste is much less radioactive, and then by then you make different kinds of reactors and do the waste of the waste of the waste, use that as fuel, and in the end clean up the whole thing. But what I don't understand, which I hope the physicists here, Ronchetti from the CERN and Cinotti here, is, does this mean that the second law of thermodynamics doesn't really work? And it's wrong, because somehow we don't go, you can get to a point where there's almost no thrown out heat, or am I wrong? Probably wrong. So I'll leave it to you. And Eleonora Marengo will now take care with great precision and passion, or having people up on the stage and doing the thing. So Agnieszka and the other people that you will be inviting up to the stage. Thank you.
So as mentioned by the director, I would like to invite on the stage Agnieszka Kuren, who is an artist and also co-curated the event with our director. Then we will have connected, because unfortunately wasn't able to come for the morning, Ersilia Vaudo, who is an astrophysicist. And then I invite to the floor Federico Ronchetti, nuclear physicist and coordinator of Alice Run at CERN, and Luciano Cinotti, nuclear physicist at Nucleo. Thank you.
Thank you, everyone. I would like to welcome everybody very cordially to this conference that we had the pleasure to convene together with Carolyn. Thank you, Castello di Rivoli. Thank you, Carolyn, for making my dream come true to work on this very important subject for my practice, for my artistic work. I would like to also thank everybody who came from all over the world to participate and contribute, and thank you to everybody who's listening online and who's present here. What we're presenting here in the background is my work entitled Conversions, a series of works which were presented here as part of my solo exhibition at Castello di Rivoli, which started in 2021, and a fragment of it can still be seen at Castello. One room, one work, not this one, but a different one. Conversions is a very good background for a couple of questions that I've been pondering, thinking about this conference and thinking about whom to invite and who, how to contribute to this subject. I have been thinking about a question of energy as obviously powering life and making everything in the world move, and at the same time energy as a currency. And in particular, I was interested in the fact that today the contemporary political economy could be described in a way as a total cybernetics, because it's based on perpetual transformations of energy as a currency into information and into capital. And meanwhile, social energies, so the way that people express their feelings and emotions around the globe, are mined by corporations like Meta, like Amazon, like Google, Alphabet. These energies are mined just like oil, I mean on a par with oil and gas, with algorithms, with artificial intelligence. And so in a way we could say that social energies became part of the global energy market. And it became really interesting for me that the digital capitalism, the economy of digital capitalism made a couple of concepts that were earlier developed in human thought as a hypothesis, as a fantasy, as a theory of alchemy, for example, or many scientists or experimenters. Some of these theories were to some degree realized or are being challenged in digital capitalism. And one of the kind of dreams of humanity since antiquity has been the possibility of construction of a perpetual motion machine. So a device that would produce energy, free energy, unlimited free energy. And the concepts, the thermodynamics, the second law of thermodynamics clearly proves that this is something impossible. And it has been proved by many scientists over time. However, people kept over centuries trying to invent this device. And today we're coming to a situation with cryptocurrencies, for example, and with mining of social energies, where there is an interesting continuity of this discourse around perpetual motion machine and free energy. Because in order to power computers, in order to power server farms, and to use artificial intelligence and very soon also quantum computing, we mostly need energy to power these computers. And now with production of cryptocurrencies, the use of energy, the cheapest possible energy, has been really important because cryptocurrencies are based on production of a use of energy to create value using computers. And of course, minerals that are extracted in various mines are very important for the functioning of computers. So there is hidden labor in this. There's slave labor of people working in Asia or in Africa mining these rare earth minerals. But at the same time, energy became really important, and this race for the cheapest energy sources has involved different cryptocurrency farms, for example, moved to Venezuela or later to China, using decommissioned water dams and hydroelectric plants to power the computers. China has famously banned the mining of cryptocurrencies a couple of years ago because of its entanglement with the energy industry that became really problematic. Obviously today there is questions of how are we going to power the AI industry, the computers, the quantum computers. So I've been thinking about this, and so this series of works, Conversions, is based on using artificial intelligence algorithms that I used collaborating with computer scientists, to mine how people around the globe are expressing their feelings and emotions of protest, for example, and desire to change the world, how they are posting about the ideas of changing the world and protesting against things that they don't like and would like to change. So we were monitoring with algorithms various social media feeds of millions of people around the globe, and the result of this monitoring and harvesting was sentiment analysis algorithms with artificial intelligence. It was aggregated, and then these aggregated results are powering each of these paintings. The paintings are executed with liquid crystal paint, and as you may be familiar with liquid crystals, they are used in LCD screens and your computer screens, TV screens. But I worked with a physicist and cosmologist, Malcolm Fairbairn from London, from University College London, and we have used this pigments that include particles of liquid crystals that are changing and transforming. So what we're doing, what I'm doing here in these paintings is essentially collecting social energies of how people express their emotions and feelings around the globe about changing the world, and then these energies are converted into electrical and thermal energy, and this is causing changes, physical changes in the painting. As you can see, it's here on loop in real time, and they are subtle, but they are happening constantly. So these paintings are alive, and they are reacting to the collective footprint, collective social capital, and people collectively trying to change the world. And things that were really important for me, thinking about this work and also this conference, questions of energy as a currency. They are related to a long history of thought around this subject, which, for example, already in the 1870s, there was a sociologist, Ukrainian sociologist, Sergei Podolinsky, who was trying to persuade Marx and Engels that energy is a better principle of value than embodied labor. And this concept has later inspired a lot of thinkers, and then there was a whole movement that proposed this idea of energy as a better, more constant, more constant principle of value than labor. So this whole movement was called energetics and then neo-energetics. And what is interesting for me is that we are currently, with digital capitalism, revisiting a lot of these ideas. Another thought that I wanted to share with you is related to the questions of how energy that I'm exploring in my work through the notion of collective intelligence, which most of my work relates to. So how everything in the world, we could say, is a product of collective intelligence, from the ways of like how minerals, geological formations are formed through coming together of molecules, of particles, through weather phenomena, through collective behavior of animals, bacterial colonies, viruses, to obviously phenomena happening in human societies, languages, writing systems, tools, social movements, civilizations, and so on. And I've been exploring it throughout my work, and of course conversions are also an expression of collective intelligence, and thinking about how in the future art maybe will be made collectively, kind of in an analogy to how Wikipedia as a system of knowledge production is a product of a collective intelligence with many contributors. So thinking about energy, I have thought a lot about questions of utility grid, which is, to me, a symbol of social ties. It is a form of a commons. And today we are experiencing very, this phenomenon that I'm about to talk about, for me, kind of epitomizes the complexity of the energy problem today. So this phenomenon is called the utility death spiral, or utility grid death spiral, and this paradox that the utility grid, which is responsible for distributing electrical energy to individual energy consumers around the world, this utility grid, which is supposed to be a commons, although some utility grids are private, but it is something that we, now should have access to. Now that many people are trying to use, for example, solar batteries or wind farms and so on, the people who are buying solar batteries are opting out from this utility grid because they are trying to produce clean energy. And of course, it's a good thing, but the complexity of this situation is that the use of this individual solar batteries is causing of all these people no longer participating in payments into the utility grid. So the utility companies or countries that distribute energy get less money from energy consumers. And as a result, the prices of energy of the utility grid are going up for individual users. And so, of course, it's hitting the poorest people. And so this is a problem, that is unresolved, that kind of shows the complexity, both philosophically and ethically, that the new transformations of clean energy are presenting. That in reality, the transformation to, for example, solar panels or any other form of clean energy, in fact, would need to happen collectively, and if everybody did it at the same time, or if there were like grouped plants of solar panels serving the entire society, it would be much simpler. But when this is based on individual people opting out of the grid, it's actually potentially leading to a social inequality for people who wouldn't be able to afford to pay for energy grid. And another example of this kind of problem is the fact that, of course, there are countries that do not have equal access to energy. They don't have utility grids, or they have dysfunctional utility grids. And basically, currently, there are companies like, in Turkey, there is a company called Car Power, and also Mitsubishi is undertaking this kind of attempts they use ships that are stationed on the sea and that are delivering power to countries that don't have utility grids, such as some countries in Indonesia, Sierra Leone, Ghana, and other places, and it's a completely uncontrolled process. It is essentially an example of extra statecraft, as it's been named by Keller Easterling. So we're getting to this kind of situation that we are faced with a lot of complex situations, especially when cryptocurrencies are produced using green energy. And so when we are using wind turbines or solar panels to go straight from this to produce cryptocurrencies, we're dealing with a situation that interestingly gets closer to a perpetual motion machine or creation of free energy, although we know that it is impossible. And these are some of the questions I would like us to also explore during this conference, and I welcome you all very cordially. And now we're going to watch the contribution of Ersilia Vedova that will be played on the screen here.
I just would like to add that at the end of the morning, from 12 o'clock onwards, we are also opening the exhibition of Renato Leotta, Posidonia, on the theme of Posidonia. It's Concertino per il mare. Renato will also be speaking in this conference just after lunch, and it will be on the second floor of the old Juvarra building, the one that we're in. So now we will watch Ersilia, who had to be in Trieste today, a short 5-minute, 10-minute video, and then our physicist will explain everything. So Federico, I would actually move you to the right of Mr. Cinotti so that you two can see the film. Thank you. The connection.
I am an astrophysicist as background, and I work at the European Space Agency since 1991, so more than 30 years. I would like to go straight to the magic of the nuclear energy that has the power of harnessing the atoms, what is inside the microscopic world. We should go back in time to understand really what there is behind nuclear energy and go at the beginning of last century. So we are talking about 1905. That was defined as annus mirabilis. And this is because this year Einstein, publishing 4 papers, was able in few months to completely change our perspective on the universe and the physical world. In a shell, what Einstein was putting on the table in the special relativity is how the behavior of reality changes when we travel at the speed close to the speed of light. Speed of light was clear at that time is a constant in the void and has an unpassable limit. And this changed in the way the perspective that Einstein put not only on space and time, that because of these facts are now linked forever, but also the perspective on mass and energy. It starts from a very simple consideration. We know by experience how difficult it is to push a trolley full of stuff in the supermarket. And more energy we impress to the trolley, and higher will be the speed of the movement. Of course, it depends also how heavy is the trolley. So the relation is very simple. The energy is equal to the mass multiplied for the speed of the trolley square. If we push the trolley, the speed will increase, but there will be a limit. When the speed will be approaching the speed of light, it cannot go beyond that. This means that all the energy we keep putting in pushing the trolley will go somewhere else. And where it goes, it will go in only the other physical element in the equation, meaning the mass. So we have that with the simple reasoning, energy and mass are the same thing, and the exchange rate between energy and mass is just a mathematical factor, and is the speed of light squared. This is extraordinary. We have mass and energy become manifestation of the same reality. And another way to say it is that the energy trapped in a mass can be unleashed, and the other way around, from energy, a mass can appear. We could say that, for instance, if we are able to convert 1 kilogram in energy, we would have the energy to supply 100,000 ohms for years. This is unbelievable, and again, is something that was not so easy to accept at that time. A movement that becomes an object and an attribute that becomes a body. Now, both fission and fusion are nuclear processes by which atoms are altered to create energy, just by using this magic formula of E equal mc squared. But there is a big difference between the two. Simply put, fission is the division of an atom into two, and fusion is the combination of two atoms into a larger one. Very opposing processes, and therefore very, very different. If I can summarize the difference between the two processes, I would say that in fission, we have a heavy nucleus breaking up to form two light ones, and then from these two light ones, we have neutrons generating that will travel with the high speed, and we create a chain effect. In the fusion system, two nucleus combine to form a heavier one. There is no existence of fission in nature, while we experience the nuclear fusion observing our stars. In the sun, the combustion process is exactly the magic of E equal mc squared. Nucleus of hydrogenous squeezing and creating helium and some neutrons. And the energy that is unleashed is the amazing energy that our own stars can create. The fission involves a chain reaction, which can also lead to dangerous meltdown. There is no chain reaction involved in fusion. As I said, fission means that heavy nucleus are bombarded with neutrons, and the most used one is uranium-235, while to merge light nuclei in the fusion system, you need very, very, very high temperature and pressures. Now, the nuclear waste, which is one of the major issues here, that are a byproduct of fission, of course, are an environmental challenge, while with fusion, there is practically no nuclear waste. And another important difference is that the raw materials for the fission, which are essentially uranium and plutonium, are very scarce and very costly, while the raw materials with fusion are essentially hydrogen atoms, are very, very easily sourced, and the fusion reaction can really be clean energy. Now, why we don't have then a fusion everywhere at the moment? The problem is that, as said, to achieve a fusion reaction, we really need extremely sophisticated technology, new technologies like, for instance, magnetic confinement, because we are talking about a plasma that can reach 150,000 degrees that should be contained, and if it's not contained, it will melt everything around, and a pressure that is able to trigger this fusion reaction, to push the atoms one into the other. And this is a technology that so far is still in the making. Last year, at the end of last year, in 2022, there was the holy grail moment of some nuclear fusion that was reached by physicists in California. A fusion ignition was achieved and was able to produce more energy than the neutrons needed to create the fusion. But this only lasted a billionth of a second. And still the energy used was not outpowering, outnumbering the number of energy that was used to inject and to ignite this fusion. So there is a lot of research. At the moment, there are more than 30 different fusion energy projects across the world underway. One of the most important is the International Thermonuclear Experimental Reactor, the ITER, which is a joint fusion experiment in France, is an international cooperation. That should be able to start fusing atoms in 2025. Still is not defined how this energy, in case we were able to create, will be converted in electricity and with which kind of efficiency. And also Germany is very active in this and is investing enormously now in fusion, as well as UK and China that have their own experimental fusion reactors. The Financial Times published a few weeks ago an article that highlights that the race to develop commercial nuclear fusion power is heating up. And the problem, the difficulty is really in the safety. Is because it's very safe that is very complicated. When we have ignited the fission process, it goes. And it goes meaning that there is a chain effect that allow the process to be alive. But of course, if you lose control, it can become problematic. Fusion instead needs optimal condition to work. And if you change just a little bit this condition, it just turns off. So it's very safe because if something goes wrong, it stops, but is much more complex. We have to think what's the challenge, the technical challenge of bringing and keep a plasma at 150,000 degrees, keep it confined to avoid that it escapes and melt everything, and also to reach sufficient pressure to ensure that the atoms can have a high probability to interact. And also it's not so clear how to transform this energy in electricity and with which efficiency is still to be seen.
It's on? Okay, perfect. Okay, good morning. Just waiting for the slides. So I'm Federico Ronchetti. I work at CERN. I will not discuss my work here. I will just try to give you some basic facts so that you can maybe decode all these discussions in a better way. But before I start, I just would like to thank the organizer for this opportunity to speak. Then I would like to just catch up what Stefano mentioned about communication. So In this talk, my point is not to give you sterile notions, but just to enable you to better communicate with us scientists and all together, because we need to get rid of a lot of ideology and a lot of miscommunication that happened in the past. So let's first discuss atoms and nuclei. There are two different things. Nuclei are much smaller. Basically, an atom, the simplest atom is hydrogen, has a positive charge at the center of it, and then there's some negative charge, the electron spinning around. We have more complex atoms, carbon, oxygen, nitrogen. Then we have the nuclei. The nuclei, it's the core of the atom is much, much, much smaller. And so there's not such thing like atomic energy. Atomic energy is chemical energy, fundamentally. Nuclear energy is the energy that comes by doing something to the nucleus. Atomic energy, in principle, is a chemical reaction. Then there is something also inside the nucleus, but I will not discuss this today. Let's check a bit the concept. So if an oxygen atom would be as big as a tennis ball, a red blood cell of our blood would be as big as Manhattan. Okay? And the nucleus, so not the atom, the nucleus, so this stuff that it's at the core of the atom will be a sort of sand grain sitting in one of these offices here. So this gives you the scale, and you can understand why nuclear energy is so powerful, because it's energy that is densely packed. But what is energy? We are always saying this word, but do we really understand what we mean? So energy is the capacity of a physical entity to perform some work. And then what is work? Work is the displacement of a force. So what Sisyphus does, it pushes this big rock up, and what it does, it works against gravity. It moves the point of application of this force from here to here. And then the thing falls down, and the energy that it gained when the rock is here, that's potential energy. And when it releases the rock falls down, it becomes kinetic energy, and then it starts it over and over. But something happened. Heat was produced. So this process is not reversible. There is a loss here. So energy can take many forms. I showed you here some of them. Kinetic, potential, I mentioned. Nuclear. Ionization also is a very important form of energy, where we strip off electrons from atoms. And heat. Heat is also energy, but it's energy with the degraded capacity. It's like having a currency that doesn't have any pouvoir d'achat, any economic value, like, I don't know, very poor country currency. So this is the concept of entropy, which is also very important. Then, sorry, I went too fast. So there was the nice introduction about fusion and fission. So how do we get energy out of the nuclei? By fusing them or by breaking them. In the end, what happens is that we have released stuff, and the difference of the energy from the initial state and the final state is the binding energy of the system. And this is very high in the case of nuclei. So you see here, this is how the nuclei is heavy on the horizontal line. So you see this curve. If you fuse elements, it means you go from light elements to a bit heavier elements. You get this advantage of released energy. If you break elements, you go from, say, uranium to smaller byproducts, then you get this amount. So you see the amount from fusion is much higher than the amount of fission, but still the amount of fission is enormous. I remind you that the bomb that was dropped on Hiroshima was 15 kilos of uranium. So the energy released from nuclear reaction is basically a direct consequence of the relativity, as it was said in the previous talk. So it's basically mass that is converted to energy. and that's why it's much larger than the chemical reactions, so million of times higher. What is this energy in the end? It's just kinetic energy, so speed of the particles that are produced, and this speed becomes heat. It's released as heat, and heat then can be used to make water boil and to run a turbine. So is it dangerous? Depends. Is it chemical energy dangerous? If you fuel your car, I don't think you feel unsafe. You refuel your tank and you go. If you throw a light match in a tank of gasoline, then you may feel unsafe. So it depends, as Stefano was saying, it depends how we use it. The same is for nuclear. We can use it for civil purposes to produce carbon-free energy, or we can make a bomb. It's up to us. Then I want to give you a few concepts about radiation, because also here I think it's very complex and there's a lot of confusion. First of all, I want to say that radiation can be thought as energy that travels from a source to a target. We have very many kind of radiation. Electromagnetic energy, light, is radiation, and it's propagated via electromagnetic waves. This can be ionizing or non-ionizing. What does it mean? It means it can break atoms or not. If it breaks atoms, then it's dangerous, because it can break also the atoms that make the molecules and the biological molecules, and you can have biological damage. It does not happen always. If you use your cell phone, that's not ionizing radiation. This light is not ionizing, but it can release heat still. Anyway, it will not damage your cells. And then we have radiation in forms of particles, usually are this kind of particles. I will discuss them a bit later. And these are all ionizing, so they do break atoms. Basically, these different kind of radiations can induce biological damage. They can be shielded with different techniques. In general, neutrons and gamma rays, which are a very high frequency form of light, are quite dangerous because they are neutral. They don't carry electric charge. So they do break nuclei, and they pass through materials in depth. While these other forms of radiation, they can be stopped quite easily. Another thing that I would like to mention is don't confuse radiation in general with contamination. Contamination means that we have radiation in an unwanted place. So if we fire an atomic bomb or a nuclear bomb, then of course you contaminate. Chernobyl is an example of contamination. If we run a nuclear power plant, we manage the process. So there's no, let's say, contamination in the strict sense. Then let's discuss a bit what means biological damage from radiation. I want to go into this because I want to show you that radiation is a risk as any other thing in life. There's no such thing like risk-free activity. I can sleep now and break my ankle, or anything can happen to anybody. You smoke, some of you smoke, so that's risk. Basically, if we have a radioactive source, we can define the activity of the source as the number of particles that the source shoots at any second. So it's like a machine gun is firing bullets, and this is the activity. The dose is the energy absorbed by the target. So the target receives these bullets and absorbs them, and this energy released. And the effective dose is the damage. So the damage is different. So here, these radiations, they have different effective, different biological damage. These alpha rays are harmless if they are outside the body. They can be very dangerous if they are inside, for instance, while those are quite dangerous always. So radiations have different capability to do biological harm. But this harm is, I will show you, is comparable to risks that we take every day. So how do we handle this? First of all, let's understand one thing. Radiation also occurs naturally. So we have radiation from cosmic rays, because we have supernova exploding in the galaxy that send very high energy particles up to the Earth's surface and also beyond. We have radiation coming from the soil. We have radiation coming from natural isotopes that we eat in foods like bananas or Brazilian nuts or many other foods. Then all this amounts to a background that we absorb every year. So every person everywhere, without doing anything, just living, absorbs this. Our body is quite well equipped to deal with this. Our cells can self-repair. They are quite capable of absorbing low doses of, let's say, chronic exposure. If you have strong doses of, prompt exposure, then it's another thing. But as we said, we don't want to make bombs here. We want to make good use of this energy. This is a map of the exposure to cosmic rays in Europe. So clearly, if you live on the top of a mountain, you get more radiation. No power plants, no bombs, just from space. If you are on a flatland, then it's less because you have more atmosphere absorbing this rays. And as I said, from food, some calcium carbonium isotopes are radioactive. This carbon-14, it's an isotope that it's mixed with the normal carbon atoms that we have in the metabolism, and it's radioactive. And when we die, this intake stops, and then it starts to decay, and that's why it's used to make carbon-14 dating. And potassium-40 is the same. It's in some foods, and we absorb it, and then it emits gamma rays. Then finally, I come to the concept of risk. So I try to show you that any human activity is potentially dangerous. And we have this concept of risk, which we understand in an intuitive way, but I would like to make it a bit quantitative. So what's a risk? A risk is a danger, probability of a danger that you multiply for the probability of a failure. So imagine a tiger. If you go to the zoo, the tiger is behind the cage. So the tiger is dangerous, so the risk is 100%. But if you put the cage in front of her, then I would estimate that the chance that the cage breaks or something happens, it's 1 over 100,000, then the risk is 0.001%. If you go for a safari and you start walking around by yourself, then maybe the risk is 100%. So risk zero does not exist. It depends always from the policy you implement. And I think we need to have an approach that is rational to risks and also to the risk connected to nuclear energy, which are, as it was also mentioned, can be made not different from everyday risks. I think I will stop here. The conclusion you can read from yourself.
When we use photovoltaic or wind energy, this is promoted by sun. And also fossil fuel originated from the sun, and the sun is a nuclear fusion reactor. At the same time, we produce 10% of the world electric energy with the nuclear fission reactor. And also part of the geothermal energy comes from the decay of uranium and thorium. But especially in Italy, there is a low acceptance of nuclear power, and in particular in the 80s, the press and the political party spread fear around nuclear use. And some light that you can see in several towns in Italy. But which is the result of that? The result that we have imported a lot of oil and gas. We have contributed to the strong increase in the CO2 in the atmosphere. We have polluted our cities. We have weakened the Italian economy and the Italian industry, and we have blocked the development of nuclear science and research, and even lost a lot of pre-existing knowledge. In the 80s, more than 90% of my colleagues working on nuclear have abandoned the nuclear activity, doing other jobs. I remained working in the nuclear field mainly because I read a publication, a German publication, presenting the problem of climate changing, and a very interesting article explaining the effect of the CO2 into the atmosphere. And even if at that time nobody cared of those facts, this article was convincing for me to think we had to come back again to nuclear power sometime. I did not expect it to wait more than 30 years. But the result is also that in Italy, we import electricity from the surrounding country, and most of that electricity is nuclear electricity, which may come from France directly or from Swiss, but is also electric energy coming from France. So now it is clear to everybody that energy is a real problem. And we are looking again also to nuclear fission. The first artificial nuclear fission reactor was done in 1942 by Enrico Fermi, as we well known. We must to say artificial nuclear, because in the past we had natural nuclear reactor operating, especially in Gabon. Yesterday, most of you went to visit the Trino plant. So it is impressive to look at the progress from the first reactor of Fermi. After 20 years, we had already under construction this plant, which operated quite well. This is impressive, 20 years development. Which are the characteristics of those plants? You know that it is cooled by water. Water is the simple technology, obvious, to be used, but to cool the reactor at a relatively high temperature, because after you had to transform the heat in electricity, so you need to stay at a relatively high temperature. To keep this kind of reactor at about 300 degrees, you have to keep the primary system at 160 bar. And with that, in the steam generator, yesterday you could see the head of the vessel and the head of the two steam generator. in the steam generator, we can produce steam at 60 bar. Obviously, the system is under pressure. So if you have a break in one tube, or you leave a valve open, stuck open, you will leave your water. So the core will be not more submerged by water and can heat up. And in a string case, we can have a core melt. So to avoid this, what we do, we have protective action. We have pumps which can introduce additional cold water. So to do this, we need electricity. This was the status of the first pressurized water reactor. Obviously, even light water reactor can be improved, and I spent at least 10 years in improving light water reactor, design new system which do not need electricity to cool the core even if you have an accident. So a huge program can be done also in the light water reactor technology. But with Stefano, we decided to make a jump, a great jump, going to a system cooled by lead. If you use lead instead of water, what happens? Lead has very high boiling temperature, about 1,700 degrees. So practically lead cannot boil off. And the reactor will be always submerged by lead, and the primary system will operate at atmospheric pressure. In addition, because this vessel is very thin, and there are cases for light water, in case of light water reactor, you have vessel thin like that, but in our case, it's thin like that. You can even imagine to add an additional safety vessel, so two vessels, one inside the other, in case we have a leakage on a weld. Can happen that in weld which is not well done, in the time to have a leakage, and if this happens, we'll have a second vessel to keep the coolant. So in this configuration, it will be practically impossible to lose the primary coolant. In terms of control of the system, as some of you visited Trino, as I said, you have seen the last part of a control rod. Also, in our case, we will use control rod to control the reactor, but because we are in a fast flux, the situation is much easier. We can put the control rod outside the core. So our reactor will be operated with the old reactor having the active system controlled by logic and by the operator. And this system will be operated at about 500 degrees. So 200 degrees more to have better efficiency in the transformation from heat to electricity. But let us suppose that the operator is sleeping, that all the logic are failed, that you have a virus in the logic and nothing will operate. What will happen? The temperature of our reactor goes up. It goes up to 600 degrees, 700 degrees. At structural level, we don't care if it goes up to 700 degrees. But we can use this 200 degree difference to provoke the intervention, to set up the intervention passive system. So we'll have a second level of control, I will say. For instance, the expansion of the core. The core will expand with the temperature, and this can bring to a reduction reactivity. But there are plenty of solutions that allow us to shut down the reactor playing on this 200 temperature increase. You can have a melt of some system and so on. So you have a second level of protection where the operator cannot intervene, even if he wants, because we want to be sure that even if in the control room there are somebody who wants to make a disaster, he cannot. And I remember when I started to work in the Safety Authority, the first exercise that I had to solve was, you are in the Carorso plant. In which time, and you are in the control road, how much time do you need to create a severe accident? In that case, I can reply, I will not able to create a severe accident. But let us go to the waste problem. So, in light water reactor, prison light water reactor, we use only 0.5% of natural uranium. So, in conclusion, we suppose that we mine 1,000 atoms. Within those 1,000 atoms, there are 7 atoms which are 235 that can be burned in light water reactor. The 238 cannot be burned. So in conclusion, what we do, we send the natural uranium to the enrichment plant, and we get rid of 90% of the fuel. So this is the so-called depleted uranium, which has no commercial value. We don't know what to do with it. And obviously in the depleted uranium, because the separation is not perfect, they will have still few atoms or 2, 3, 5 remaining. So the 10% of the fuel is used with the enrichment, with a content of 235 of about 4-5%, which is enough for prison light water reactor. We are allowed to go up till 20%. Otherwise, we are supposed to create bombs. So, but in conventional application for electricity production by the atomic energy rules, we are limited to 20%. But in fact, in light water reactor, we need only 4-5%. And those with, so this 10% of the original fuel enriched at 4-5% will be used to feed our reactor. So in our reactor, we'll produce electricity and we will fission the 5 atoms of 235. Those atoms will be split in 2, and the two particles will be the so-called fission fragments. But some atom of 238 will absorb a neutron coming bigger. So, in particular, what is the most important is plutonium. So, in the spent fuel, we have about 1% of plutonium. So, 5% of fission fragment, 1% of plutonium, some small fraction, very small fraction, minor actinides, so americium, curium, and the most part remains as uranium-238. So what we do with this spent fuel? We don't know what we do. This is the reality. The idea is to send it to a geological depository, but practically in all the country, this spent fuel is stored near the plant. So a small quantity, but a storage near the plant till the day that the government will decide for the final disposal. This is what happened in most of the country, and so this is radiotoxicity of the spent fuel during the time in comparison to the natural uranium from which we started, because also natural uranium is radioactive. There's an exception, which is France. France, instead of keeping the fuel nearby the plant, send the fuel to La Hague to reprocess. So, and practically, at La Hague, the spent fuel is separated in 3 groups. One group contains the fission fragment and the few minor actinides, which is vitrified to be sent to a future geological depository. But the quantity very, very, very limited. The uranium is kept, and the plutonium also is separated and partially recycled, but only partially in light water reactor. In fact, France, waiting for fast reactor, is obliged to recycle plutonium separated in light water reactor, but in light water reactor we can burn only, let us say, about half of plutonium. So we can burn in light water reactor the isotope 239 and 241, and not the 240 and 242. Now, if we go to a fast reactor, the situation is different. With the fast reactor, we can burn practically everything. And this is, oops, sorry. Oh, why? Okay. So, in a fast reactor, we can burn the depleted uranium coming from the enrichment plant. We can burn the uranium from the spent fuel after reprocessing. We can burn plutonium, and we can burn minor actinide. So we can produce the electricity and to leave only fission products. This is the situation. So nowadays, with a molecular reactor, how we are designing, we can immediately skip from the red curve to the blue. So burning all plutonium. This is possible today. And with additional technological development, will be possible in future to burn also the minor actinide, because you have seen that in France, minor actinide are not yet separated for the fission fragment. So we had to separate also the minor actinide for the fission fragment to be recycled. In that case, we'll have a fission fragment which will have a lifetime of 250 years in comparison to natural uranium. So from now to 250 years, the radiotoxicity will be higher than the natural uranium, later will be lower. But you have to keep in mind that the quantity are very small. And some of the fission fragments are very interesting industrial elements. So for instance, rhodium and palladium. There is plenty of rhodium, palladium fission fragment. And those type of elements are very important for the industry. Rhodium has a cost which is not far from $1 million per kilogram. And so in future, it will be one that this fission fragment have decayed, it will be quite easier to extract those products. How much fission fragment do we have? We will produce 100 fission fragments per terawatt electric production. Italy needs 300 terawatt electric per year, roughly. So 300 terawatt electric multiplied 100 kilogram, or if you consider what say our physicists, not exactly the same mass of fission fragment and uranium in input, but the difference so small that for the moment, let me say that quantity of uranium that is needed as an inlet is the same quantity. I'm engineer, not so rigorous than the physicist. So in Italy, to produce 300 terawatt hour, which is the total consumption of energy, we will need 30 tons of uranium per year. If you consider it is about 100 euro per kilogram, 3 million of natural uranium per year will be enough to produce all the electricity used in Italy.
Thank you very much to Agnieszka Kuran, to Federico Ronchetti, Ersilia Vaude, Luciano Cinotti, that so kindly introduced us to the topic and share with us all the information that we might already have or may not. I would like to call on stage Sofia Kundale, who has prepared a special performative reading for us and is eager to present it today. So please, Sophie.
First, I just want to say thank you to Energy Cultures for this conference and experience. I will be presenting extracts from my novella in progress, Half-Life, an erotic science fiction about a woman who falls in love with nuclear waste. Chapter 5, The Shell. A tumbleweed the size of a car had interrupted Pearl's journey to work. It had freed itself from the ground or a crack in the building and gathered strength in the high winds, picking up rocks and debris in its potentially radioactive tendrils. By the time it collided with Pearl's hatchback, it was a formidable force. As summer transitioned to autumn in Hanford, the winds would start their swirling. Pearl had heard about the winds. They were famous for their challenging nature, their ability to drive people away. For the mass of workers who first lived at Hanford, it was the intensity of winds whistling through their vulnerable prefabricated houses that broke the collective camel's back, causing them to leave town in droves. Hanford was a chosen place, an unwilling sacrifice. The only site in the US that could match the requirements to arm the country with world-ending force, said the man tasked with finding it. That it was occupied by thousands of families and a tribe with ancient claim was deemed a solvable inconvenience. When the army swept in like a bulldozer to clear the land, they were given just 30 days to pack up their entire lives and go. As a chill touched her bones, Pearl could not help but feel these hostile, harsh winds as the souls dispossessed by war. The tumbleweeds that haunted their land, a tangled knot of spines, bent out of shape by force. Sometimes the wind would swirl into dust storms, spinning columns of ashes. Pearl fought her way to the lab head first. She a waif, the wind so strong. It pushed her back as if to rewind her. The summer that was yesterday was hard to imagine even now. Its pink skies and bleak pastels washed out and bloodless. The winds that had arrived to the landscape like the spots of blood that bloomed on Lady Macbeth's hand. Out, damned. But the harsh slap of cold had released her from the curious depth of her dreams, which came heavy and dank each night, covering her in pools of sweat. Abstract forms giving way to clear visions, opening her eyes and cleaning them with tears. But the harsh slap of cold had released her from the curious depths of her dreams, which came heavy and dank each night, covering her in pools of sweat, abstract forms giving way to clear visions, opening her eyes and cleaning them with tears. But the harsh slap of cold had, cleaning them with tears. She shut the metal port of the laboratory behind her, exhausted and incredulous that all she had done today was wake up. With a long, exhaling breath, the significance of this particular day began to dawn on her. The team entered into their whites as if preparing for a ceremony. Their suits were numbered, together a hive mind, a quantum computer, all tasked with the same operation. Tank SY-101 was being transferred into a new shell, a highly technical and difficult procedure. Its single shell of mild steel was corroding, growing frail like aging skin. The team were working hard to remove the waste to a new double shell tank made of stronger stainless steel. Taping the hazmats with duct tape to their boots and gloves, the sterile nature of their dress did nothing to disguise the reek of nerves that enlivened the air. A febrile concoction of vertigo, stage fright, birthdays, lucid prayer and panic. They drew upon the experiments they had conducted like mantras. Logic would absolve them, data would absolve them. Equations and numbers forming a force field of lucid faith. SY-101 was one of the 177 gargantuan tanks of radioactive waste that lay buried underground at Hanford. Each tank was an entirely unique and devastating combination of elements, leftovers from the Manhattan Project and the Cold War, where nuclear weapons were being produced with maniacal speed. The Hanford site was home to the B reactor, the largest cog in the machine of plutonium production. Numerous violent chemical processes were used to separate this precious element from the uranium that bore it. The tanks of waste were the dregs of that operation, an unwanted product from a time when winning meant more than life itself, the motherless offspring of Little Boy and Fat Man. Left to rot untouched, the tanks had evolved a life of their own, becoming more deadly and complex, like how Frankenstein's monster, shut out in the cold, grew a bloody conscience. Each was now a unique combination of elements, exhaustive inventories that had once been kept for each tank, salts, acids, and oxides used to strip out the plutonium, now served only as vague clues. Besides these chemicals were much more random and accidental elements. Fallen hard hats, dropped lunchboxes, dead bugs and birds, tons of diatomous earth, created from the fossilized remains of tiny aquatic silica-bodied organisms. A collection of poison balls intended for the unlucky mouths of those lives caught short and fateless in the midst of a nuclear shutdown. Contaminated and failed hardware. Pearl imagined that perhaps it was a single element of this detritus that had made its way into the shell and catalyzed the indescribable something that was now SY-101's insides. Something as insignificant as the fibers of a lost glove, the sole of a worn boot. No, a single eyelash that had fallen through the portal and created a monster. How a fly sullies an entire soup. She thought further of a pearl's beginnings, how a foreign substance slips into the crack of an oyster between the mantle and the shell and creates an irritation, causing the oyster to protect itself by producing nacre, an organic crystalline matter, to sheathe the foreign matter in iridescence. Over time, these smooth layers form a pearl, an irritation, a shining little aberration. Erasmus Darwin once wrote, "E conscious omnia," everything from shells. Pearl felt, everything from dirt, was perhaps more accurate. Tank SY-101 was now threatening to explode. splattering its highly radioactive content over the desert, poisoning everything in its reach. The thick, viscous nature of its toxic colloidal contents were backing up and clogging the lines, putting enormous pressure on their points of connection. Panic simmered among the scientists in the observation zone, who had predicted and prayed that this would not happen. Pearl watched on, choked with butterflies, as the engineers in plastic hoods and oxygen tanks crowded around SY-101, which was being penetrated by metal tubes and elaborate pump systems as if it were on life support. The scene was evocative of death and discovery. Surgeons round a body, astronauts discovering a new planet, archaeologists unearthing an ancient sarcophagus. SY-101 was a sphinx, its chemical makeup endlessly bearing new riddles. The millions of dollars of engineering, the infinite brain power and perspiration invested in decoding it was falling short. A system that by all calculations should have succeeded seamlessly was now being hastily sewn up and aborted. SY-101 showed their fallibility, their hubris, teaching them time and time again to fail better. For this reason, it demanded the most attention from the scientists, their Pavlovian fascination, a moth-like dedication. Its crust was a crunchy, hard salt cake, creaking and peaking with the frequency of icebergs, undulating and bubbling like clouds. Beneath, a thick and Stygian syrup, studded in streaks with crystals and calcifications, acidic, caustic, boring a hole in its shell to escape, forever becoming something else. Pearl liked to gain a holistic overview of her subjects, to zoom into the atoms and out to the stars. Bearing witness to the tank's defiant matter, its irreverence and mysterious nature, a strange affinity began to form with the sleepy passion of awakening. A shimmer of nascent emotion, a momentary and vivid unearthing of her buried adolescence. Memories that had long since been dormant arose with the pungency of raw bile and desert flowers. Chapter 4, God's Blood. The sun is hot, the air is humid. A thin membrane of sweat covers her body, dripping from each pore and trickling southward. Pearl sheds a layer and feels freer. She licks her top lip and savors the sweet sour taste. While body odor clung to the other kids like armor, Pearl would have to sniff her clothes hard for its trace. She liked its potency, its offensiveness, and now the desert was bringing it all out of her, a sign of things to come. Soon her water bottle is empty. Only remnants of backwash cling to the side. She needs water, imagines herself surrounded by it, feels the romance of the desert, how it all used to be underwater, how that explains the sand. A mirage is the desert dreaming of its past. Her head begins to pound as if an alarm was sounding. Her clothes suffocate her. With dehydration, her thoughts become more hostile. The haunted Doomtown house from before loomed like an unmarked grave and grew giant spikes which pierced through its walls and pinned it to the earth. Words from the tour guide came back to Pearl. They waited for 0 hour. The images of the blast rolling forward to take the house repeated itself. Pearl felt that she had been walking for hours, that she herself was a soldier waiting in the dugouts. A bubbling crest of flame, followed by a growing corona. Pearl looked up, imagining the mushroom billing over her and crushing the sky. Pearl thought for a second she might die and didn't imagine her life would be so short, so made a quick prayer to God or whoever else lived up there to let her live. Clouds thickened above. The burgeoning mushroom head transformed into sweet, puffy cherubs who shielded her from the sun, their edges expanding to form a blanket, inviting her to lie on the ground, to be still and let them hold her. She lies, panting in their shade. her burning body enveloped in a blissful coolness. The air around her becomes heavy, so heavy that it holds her down. The sky roars and cracks. A slice of lightning opens the clouds. Rain, thick and fat, pounds on her body, drenching her clothes and skin. But it is the smell that wets the inside of her mouth, the erotic play of rain and earth. There is a name for this smell, petrichor, defined as the earthy scent produced when rain hits dry soil. The word is constructed from ancient Greek, petra meaning stone or rock, and ichor describes the ethereal golden fluid that is the blood of the gods. Is this the smell then? Is this the smell of earth being infused with God? The smell of prayers being answered? The earth sighs with pleasure beneath her, allowing the rain to enter its cracks and heal its wounds, relenting to a thick, even clay. She turns over onto her body. Grateful, relieved, she kisses the ground. The kiss gives way to open mouths and tongues. She begins to claw the ground, drawing thick handfuls of clay into her mouth to eat, dragging her body along like a snake through the force of her appetite. The cloying texture threatens to stick in her throat, but is pushed into submission. It was heavenly smooth, grey-brown and shiny like the surface of a dolphin, ripe meat infused with raw God's blood. To Pearl, the taste and feeling it gave her was incomparable. She flopped over and over in the rain, coating herself in mud. She was found by her father, soaking, filthy, naked, with a mouthful of dirt. Pearl wanted the earth to swallow her up, and the feeling would never leave her. That night she dreamt of being face to face with a baby woolly mammoth, its long hair moving and swaying gently as if it were submerged underwater. The baby looked at her with huge pleading eyes, glistening with innocence. She wanted to look after it, and found in her hand a shiny red apple, extending her arm to meet its mouth. The baby mammoth took the entire apple, crunching. It seemed to thank her, to smile. Pearl woke the next morning to find a reddish-brown color staining her knickers and sticking to the inside of her legs. She tasted it, but it wasn't mud.
Thank you so much, Sophie. I'm asked to share a very practical information. Since we're running a bit late, the contribution by Mark Wigley and Beatrice Colomina will be just postponed to the second session in the afternoon, so that we can be present at the opening of the exhibition by Renato Leotta. So we will just have one last contribution by designer, curator, and architect Paolo Antonelli. Thank you.
Clicker, please. And it's disappeared. Oh, it's here. It's just very small. Okay, thank you. Revital Cohen is an artist that buried, like nuclear waste, this early work of hers that she did when she was still in school. It was just the turn of the millennium. She was at the Royal College of Art. And she had created a program that would enable computer users to scratch and make their computer bleed when it kept crashing, just out of anger, an expression of like angry energy. You're talking to a curator right now, and curators are not very scientifically correct sometimes. You know, they want to express to an audience as wide as possible, especially in a place like MoMA, concepts that sometimes are better expressed scientifically by the individual objects. But as a whole, exhibitions take a lot of license. And I'm talking to you today about the first exhibition I didn't ask which one was the clicker that I needed to use, so I don't know which button it is. Oh, great. The first exhibition that opened the new building of the Museum of Modern Art in 2019 was very appropriately called Energy. And when the graphic design team of MoMA asked me what I wanted as the title wall, I said, I want solar flares. And that's what they came up with. It was an exhibition from the collection, therefore it only had objects that could be found in the collection. But I'm gonna take you through the path that my associate curator Anna Burkhardt and I went through to get to this display that was a way to open the Museum of Modern Art. And here are some views of the exhibition. We just looked at the whole collection and tried to find any type of energy that we could possibly find. So you'll see there are not really examples of transformation of energy, some others are representation, but we tried to propose the idea that design is energy and design is transformation. What I have been arguing for many years is that design takes revolutions that might happen in science, in history, in technology, and transforms them into life. But through a transformation of energy that percolates down what is studied by scientists like the one that we've heard today, and people. So with this exhibition, we were trying to show how this energy is also translated by designers into their objects. It's a continuous flow, and Ercilia was talking about Heraclitean flow of energy that is mental, that is material, that is data-based, and that then flows onto the world. This is the 53rd Street. Luckily enough, we have the IEC on-off sign in the collection, so it was great. For the opening of the new building, I could have this like MoMA is switched on again, and there was this beautiful video on this giant screen that talked about the fact that when we moved from electrical circuits to electronics, we could fuse the two buttons 0, 1 into one only. The museum was on, we were ready to transform everything we knew into new energy. So you can also see here the communication between Anna and I, and sometimes are funny, you know, we would communicate by PowerPoint. So she would say, what is the relationship between energy and power? How does design play a part in that relationship? That's between Anna and myself. And then we started looking at the whole collection and talking about, well, of course, mechanical and kinetic energy. We have a lot of coils in the collection, a lot of propellers since the 1930s, because the funny thing is the museum was interested in the gut, in the inside part of energy since the very beginning. Coils and cams and even this linky are forms of display of energy that are in the collection and that could be shown to the public. Here are examples of transformation and augmentation of human energy through screw pulls, through through fins, and also through the eye writer that was designed for Tempt One, who was a graffiti artist in LA that got hit by ALS, by Lou Gehrig's disease, and was stuck in bed. And this committee of programmers and hackers found a way to take his eyeballs and have the eyeballs command a laser tag that could tag buildings in downtown LA. He just died after more than 20 years in a hospital bed, just to tell you about his work. And then solar energy. I've seen that you have the Olafur, oh, it got too fast. I've seen that you have the Olafur Eliasson solar lamp that is in the Castello store. And so you see here various examples of solar energy, including this beautiful 3D printing machine that uses the Sahara desert sand and the beams of the sun that are concentrated by a Fresnel lens to glassify, as in a 3D printing, and an old object at the same time. And even this 1950s cooking device that was concentrating the beams of the sun so as to make hot dogs with the sun in the American desert. Other example of energy is also representations of wind energy within the collection, starting from this great visualization design, the wind map, that shows the wind over the territory in the United States in real time. You can access the map now, as if it were the wind caressing a wheat field. It also has an archive that shows you when hurricane happened, how the wind pattern changed in an ominous way. And instead, light weeds that are these digital weeds that move when people walk in front of them, and that try to really make the physical nature of energy being transformed into a digital one, and so on and so forth. Many, many objects in the collection that Anna and I gathered trying to decide what to show in the end. Objects from very early on, electrical energy, of course, lots of lamps that then we abandoned along the way, but this is the way we were thinking. How do we represent the concept of energy? And of course, electronics of various kinds, LEDs. No, it was really like a panoply of possibilities, including this idea of also showing reproductive energy through the work of, once again, Revital. This artificial biological clock is a clock for a woman to control ovulations in her life by being connected also not only to her biology, but also to her stockbroker and to her office. It's this kind of idea that we can plan everything with a clock, but in truth, we cannot really. And Typosperma, who is another representation by a graphic designer in Israel, who thought that we could maybe one day inject a letter into every sperm so that each ejaculation can become a poem. It was just like many different examples of ideas of energy. And you see here, they ranged also to furniture. Ingo Maurer's beautiful Porca Miseria from 1994. Video games, it was beautiful in that game, Czar's Revenge from 1982, an Atari game. The designer used the imperfection and the kind of like perturbation and turbulences in the CPU to actually make it into an obstacle that the player had to go through, or even representations of the prejudices about energy. That is a huggable atomic mushroom that Dunn and Raby designed so that people could hug their fears. So I'll go through just one or two particular objects just to show you how sometimes with collection objects we're able to also talk about complicated concepts. Masood Hassani grew up in a part of Afghanistan that was riddled with minefields, and as a child he used to play with his friends and with his brothers by making these paper toys that were rolling toys that would be powered by the wind, and they would roll and they would have races, but sometimes they would end up in minefields, so they couldn't be retrieved. So when he found himself at the Eindhoven Academy of Design many, many years later, and he had to choose a graduation project, he chose that. He chose to do a rolling object powered by the wind, possibly done with very cheap materials that could be found everywhere and replaced when necessary. And he created this sort of dandelion, like a hellraiser dandelion that can be pushed onto minefields, is light enough, because it's bamboo and rotation molded plastic, as to be sent into the field and makes mines detonate. Of course, this is still a prototype, but he's studied the possibilities of making it, of also putting a little engine in it in the core, so that it could actually become a deminer. As you probably know, mines cost nothing to be settled down and cost thousands of dollars to be taken out. So it could become a possibility initiated by a designer that had his own life experience teaching what to do. And it's just also very beautiful and poetic, even though it's studied in its detail to be scalable all over the world, because bamboo is also a very highly replaceable material. Another example of a great work that talks about energy is once again by Revital. She's one of my favorite designers. She now wants to be called an artist so she can pay the rent. Designers cannot really pay the rent that easily. So together with Tour van Balen, she created this choreography that tries to express the 75-watt energy that a factory worker expresses during the day. She took a London Royal Ballet choreographer to a factory in China. That was in 2013. It wouldn't be that possible today. And together with the workers of the factory, they created a choreography to express this 75-watt that culminates in this object that exists only to make this choreography possible. The video is fantastic. I can't really show it or show it online, but the fact that these workers collaborated to express what their energy output and also what their creative output could be into the making of objects every day is really stunning. And here again is Anna's comment, human labor and the body's relationship to energy systems. Let's put it all in there. We were trying to really stuff it with anything about energy that we could find. And you see here, we were also talking about this object that was by an Irish designer, fashion designer, that was supposed to be an overall. And Anna said, revitalizing constructivist ideals, but also using materials in a different way. And then this is almost like a Franken machine, framing auto reverse here in the context of electronic waste. And we kept on like really almost riffing with the theme of energy over all these different objects that we had in the collection. It's something that happens with many exhibitions, but with energy was particularly interesting. And it's very funny because Anna said, not quite sure this works, you know, so we didn't put it in the exhibition in the end. We also had other objects that we didn't put in the exhibition, although they're really quite interesting. Maybe they were the ones that were too representative, like this set of posters you see up here, A.G. Fronzoni. If you're not familiar with his work, he's a fantastic graphic designer from Milan, very obsessive, doing fabulous work, or other, quite well-known work that you might have seen 1,500 times on T-shirts everywhere, and many others expressing this idea of energy. So we try to move away from the simple or simplistic representation and be slightly more sophisticated and mediated, even though the exhibition was supposed to be for as wide an audience as possible. We even had some video games here. This is Cannabalt, which is a classic linear video game in which this guy jumps across roofs, and also typefaces that we didn't use. Not to mention examples also of architecture. This is Alex Schrader, Counterweight Roommate. This is the idea that you live, it's codependent living. You have a roommate and you are codependent because you have this contraption here. So if one wants to go to the bathroom, the other has to go into the bedroom and vice versa. There's a continuous exchange of codependent energy. Not to mention, last but not least, also this idea of creative energy. Biotopia is the first app that was in the collection by Bjork, of course, and it's all about energy. It's all also about the interaction between the creators, because it's not only Bjork, but it's many others, and the player. So you collaborate and you make energy and you make music together, and so much of the music feels like energy. But there's a lot of poetics and there's a lot of license that we take as curators. For instance, you can see it really expressed here. This was a slide by me to let Anna know, yeah, this is a little bit a chance for us to talk also about the metaverse perhaps. But it's important, and we've seen it before, to communicate to as wide an audience as possible. And the way I interpret this morning and the way I think that Agnieszka and Caroline have put it together is having two sets, two armies, two groups that slowly, slowly come together. You know, the artists, the curators, and the scientists. So I hope that this little experiment by two curators at MoMA can help you. Thank you very much.
Hello. Thank you very much, Paola. This was like a whirlwind tour. Fantastic. Yeah, in 10 minutes. And Sophie, thank you for your very, very difficult reading with a metallic object around your neck. I would like to, together with Renato Leotta, who created a work around and with and through Posidonia, a land plant that fled to the sea and that makes the most oxygen of all the plants in the planet per square centimeter, to invite you upstairs to the second floor where Marcella Beccaria, the curator of the exhibition, is waiting for us, and we will see the installation that is connected to a concert for those of you who are back on November 4th. do you want to say things upstairs? Upstairs. Okay, so let's go. And then there'll be the lunch break, and then we're all back here. Okay. Yeah, you can leave stuff here. Yeah.